Okay, so we're picking up where we left off yesterday in 2.7. On the previous page, we had filled in a chart about instantaneous velocity. Okay, what's happening when velocity is positive or negative, and we're looking at horizontal line or vertical line. Now, we're going to talk about acceleration. So, acceleration is the instantaneous rate of change of velocity. So, it's a derivative of velocity. It tells how quickly the body speeds up or slows down, or how fast the velocity is changing with respect to time. Okay, so I always think acceleration is a second derivative of the position function. It's also the first derivative of velocity. So you see lots of different options there. Just because an object's acceleration is 0 doesn't mean the object is stopped. Think about cruise control on a car. It simply means the velocity isn't changing. The acceleration function behavior can be summarized below. So, horizontal line, we'll start with that one. When acceleration is positive, what's that doing to a particle? Or whatever.
Velocity is increasing.
Right, but what's it doing to the actual, what's the object doing?
Moving to the right.
Okay, it's being pushed to the right, yes? So if you have positive acceleration on a horizontal, it means that the object, the item, whatever, it's being pushed right. What about if acceleration is less than 0 or negative? Then that means the object is being pushed left. What are options, or what are thoughts, if acceleration is 0?
It could technically be at rest, or it could be at a constant velocity.
Okay, so it means there's no change in the acceleration, or excuse me, the acceleration is 0, so it means there's no change in velocity. Whatever it's currently doing, that's what it's going to keep doing. So I'm going to write no change in velocity. Okay. Same idea, but with a vertical line. If acceleration is positive, it's going to push the object up. If acceleration is less than 0, negative, the object is going to be pushed down. And again, if acceleration is 0, there's not going to be a change. So no change in velocity. Okay. So now the bottom half of this page is what I would say is an important chart. Okay, it comes up in various, word problems, free response problems as we talk about things. The speed of an object. If you remember at the end of class yesterday, I mentioned, speed is not the same as velocity. Speed is the absolute value of velocity. Velocity can be positive or negative, but speed cannot. Speed is just positive. Now, with this in mind, when we're talking about speed, okay, the speed of an object is increasing when it's moving away from the x-axis of a velocity time graph. Likewise, the speed decreasing when the object moves towards the x-axis. Without the aid of a graph, we know the following relationships. And those relationships, if velocity and acceleration have the same sign, the object is speeding up. Okay, so you know enough to know if we're asked, is the object speeding up or slowing down? You're looking for the signs of velocity and acceleration. Same sign, they speed up. And opposite signs, the object is slowing down. And this chart just summarizes that. But really just remember, same signs speed up, opposite signs slow down. I don't think I really need to talk about the chart past that. Good? Okay, let's go read a position and velocity graphs. Okay, we're often asked to analyze motion graphs. understanding the differences between a position versus time graph and a velocity versus time graph will prove to be important. Kind of like understanding the difference between the original graph and the derivative graph. For many graphs, both the slope of the line and the area between the line and the horizontal axis, have physical meanings. So as we look here, this is a position versus time graph, meaning my x-axis is time. That's my independent variable. It's always going to be time, or time's always going to be your independent variable on the x-axis. And in this case, position, so distance, is my vertical axis. Now, with that in mind, what does the slope of a position versus time graph tell you about the object?
Velocity.
Okay, velocity. And so it does tell you velocity. One way I can think about this, okay? Slope, change in y over change in x. So change in y right here is change in the distance, so change in s. Change in x is right there, and that's that change in time. So you can think about it as change in position over change in time. Okay. And generally speaking, remember, velocity is the direction the object moves. Okay. What does the x-intercept of a position versus time graph tell you about the motion of an object?
Be at what the velocity is 0 at a certain distance.
Okay. And technically, if we're talking about like an x-intercept here, which this one's 0, but like if we had an x-intercept here, that would be at whatever time we start. That's also your, what did I have in here? Original position, I guess, is how I phrased it. Yeah, I have it phrased as the original position, but so x-intercept. I guess it does tell you about the motion of the object, doesn't it?
I mean, it tells you that it stopped because the velocity is 0.
Right. Well, wait, this is a distance graph. It tells you it's traveled.
Yeah.
It hasn't traveled it all yet.
Yeah. Technically, velocity is not 0.
Velocity would be whatever the slope of the line is. So more like the velocity at the original position, I guess. How's that? Did you take your Scantron test any time today? Okay, someone's running a bunch of Scantrons. So.
I only ever take Scantrons around finals time for the most part.
Well, makes sense. Okay, and then down here it talks about velocity. What did I have in my notes here? Just putting on here. Okay, it basically is just giving you the velocity definition there, but Reminder, when the velocity is greater than 0, the object's going to move right, and when the object is less than 0, the object moves left, which we kind of already have talked about, but okay. Okay, anything else on this graph? I think I've got everything I need on there. Okay, so position versus time. Velocity, the derivative of position, is our slope here. Okay? The bottom of this page is a velocity versus time graph, which for me, honestly, is the harder one to, I don't know, maybe you guys looked at these in physics, I bet. So for you, not necessarily, but for me, this is the harder one to process here. But let's look at this. Okay, do notice x-axis is labeled as time. The vertical axis is labeled as velocity. Okay.
You always help this with the graphs because you always have to think about the units,
Okay.
which I can explain in a second.
Okay, as in the fact that time.
So because the next one, the answer is gonna be distance, and if you think about it, meters per second times second is just meters, and distance is in meters. So that's how you would know that the area under velocity and time graph equals distance.
So time is in terms of seconds. I see what you're saying.
Mm-hmm.
And then velocity would be in terms of something like
Meters per second.
meters per second, or well, feet per second, whatever, you know.
And so when it asks the area is multiplying the two, and
Okay.
meters per second times second is going to equal meters. And what is meters? Your measurement of distance.
Distance. I like that.
Yeah.
I like that. I like that. As I said, this is, you know, and this is where I need Mr. Kevin to review my physics because it's been way too many years for physics for me. So, okay, so I never even read the problem. Let's backtrack there. Consider an object moves at a constant velocity of 5 feet per second, shown at the right. So notice, this is a velocity axis, 5 feet per second. Oh, so technically, we put meters because I hadn't read the labels yet. Technically, this is feet per second, if I want to be accurate here. Since velocity is positive, we know the object is moving to the right. How far has the object traveled in 6 seconds? So there's your 6 seconds that you're looking at. So to answer that first question, the first question was how far has the object traveled after 6 seconds? And how far is it going to travel? And that's kind of
30 feet.
30 feet because we're looking at if the velocity is 5 feet per second. And then if we're trying to find how far has it traveled, your position, you're going to be looking at the velocity of 5 feet per second times the change in time. Well, and again, I'm going to put units on here because the units definitely does help here. Velocity is 5 feet per second. Change in time is, they asked us after 6 seconds, right? And so when you go to multiply those, 5 times 6 is 30, and seconds will cancel off, giving us 30 feet. Okay, now this leads us into what Logan referred to as the first question a moment ago. What does the area under a velocity versus time graph tell you about the motion of an object? And this area is what we just found, isn't it? We just did the velocity times the change in time, and we got a distance. So I have it listed here as total distance traveled. Okay. So area under a velocity graph is total distance traveled. And I guess you could also, I don't know if you guys, I always feel like I see the distance equals rate times time formula a lot. So you could also relate it to distance equals rate times time, because it's distance traveled and it's velocity times time. Okay. Okay. What does the slope of the velocity versus time graph tell you about the object?
Acceleration.
Okay. The slope is going to be our acceleration.
So on this one, you can think the same thing unit-wise, because the slope is going to be your y over x, right? So your v over t. So you have feet per second divided by seconds, which is just feet per second squared, which is the unit for acceleration.
Okay. I like that. Okay. I also just think of it, if this is a velocity graph, the derivative of velocity is acceleration. So the slope of the velocity line would have to be acceleration. Okay. And
Here it is.
yeah.
This is the one where velocity would equal 0, right?
What does the x-intercept on the velocity versus time graph tell you about the object?
At what time does velocity equal 0?
Okay. So what time, you said what time does velocity equal 0? Okay, yeah. I have it written in mind, which, when is the object standing still, or reverses directions. But in both cases, it would be when your velocity is 0. So keep in mind, when velocity is 0, either the object is standing still, or it reverses directions. Okay. Okay. I guess a couple of different things I've written on here is just that, for instance, 5 times 6, just showing that area a little bit. That 5 times 6 was that 30 feet. And then also that here the acceleration was 0 because the slope is 0. So, okay. The next 2 pages mostly go together. Example 5 has only 28 parts. Only. So, this will take us some time to work through. Okay. The graph at the right shows the velocity of a particle moving along a coordinate line. Assume the positive direction is to the right, and v of t is measured in feet per second. Find the following. So pointing out here that this is a velocity time graph. Okay. When is the particle moving at a constant speed?
I don't know how you wanted to write it, but between times 0 and 1.
Okay. I will say on this lesson,
And if you want like parentheses or like the greater than less.
I have the greater than less things. I have inequalities in this lesson. So I have it as 0, less than t, less than 1. And it's moving at a constant speed because velocity is 5 there, right? So it's moving with a velocity of 5, so constant there. Okay? When is the particle moving to the right?
It would move from the 0 to 2. Yeah, 0 to 2.
I agree. Why?
Because the velocity is positive.
Okay, so a particle is going to move to the right when velocity is positive. This is a velocity graph. So velocity graph, the velocity is going to be positive when the graph is above the x-axis. And this graph is above the x-axis from 0 to 2. Okay, good. So in the same idea, when is it moving to the left?
2 to 5.
Okay, so when velocity is negative, less than 0, your particle moves to the left. This graph is my velocity is negative when my graph is below the x-axis. So from 2 to 5. When is the particle speeding up?
From time 2 to 3.
And why is that?
Because both the acceleration and the velocity are negative.
Okay. So, particle, remember we just talked about this on that previous chart, page before last. When something is speeding up, that's when velocity and acceleration have the same sign. So we're looking for either velocity and acceleration to both be positive or both be negative. Now, this is a velocity graph, so we can see where things are positive and negative. What do we know about acceleration? Acceleration is going to be the what on this graph? The slope, because acceleration is the derivative of velocity, yes? So, with that in mind, up here, and I'm going to erase that, but there's my positive velocity. Down here is negative velocity. I'm not going to leave those circles there because that's going to get too confusing. But I guess what we can talk about, what kind of slope do we have? Well, from 0 to 1, that's just a 0 slope, yes? From 1 to 2, we have a negative slope. Well, so none of those have the same sign. From 2 to 3, it's a negative slope, yes? And it's negative. And then over here from 3 to 5, we've got positive slope, so positive acceleration, but negative velocity. Okay? So, 2 to 3. Okay? And in that case, what we could say that velocity was negative and acceleration was negative. Okay, so what do we need for when they are slowing? When is a particle slowing down?
The acceleration is negative.
Or it's not just when it's negative. Speeding up is same sign.
So are we defining slowing down and speed? So I guess we're talking about speed in that instance?
Yes. Yes.
I guess that makes sense because the opposite is speeding up.
Right. Yeah. So when you see the phrase slowing down, think of the opposite of speeding up.
It would be from 1 to 2 and from 3 to 5.
Okay. So yeah. So from 1 to 2, we have positive velocity, negative acceleration. Okay, and that's, what did I just say? Positive velocity, negative acceleration, and from 3 to 5, we have negative velocity, but positive acceleration. Basically, the intervals we didn't give earlier, with the exception of the one that has the constant velocity. Okay. Oh, shoot. Oh, no. Okay, we've got to start going across the screen. I was like, oh, no, I was so in the habit of going down the screen. Okay, 6. When is velocity increasing?
3 to 5.
And why 3 to 5?
So the y value is going up.
Okay. I'm going to say that the acceleration is positive, is how I'm going to say it. Okay. Acceleration is positive, and velocity increasing, we want to know what the derivative of velocity is doing, what the rate of the velocity is doing. And so that's happening between 3 and 5 because we have a positive slope there. Okay. 7. I didn't put these all on one screen because it'd be hard for me to write that small, but we're going to have to do some flipping back and forth when I need to here. So 7, when is the velocity decreasing?
1 to 3.
1 to 3, because it's any time that our slope is negative, right? Acceleration needs to be negative, so 1 to 3. So when acceleration is less than 0, negative slope. Are your answers to 6 and 7 the same as your answers to 4 and 5, respectively? In other words, do 4 and 6 have the same answer, and 5 and 7 have the same answer?
No.
No. Explain.
Because the interval from 1 to 3 is messed up.
The interval from 1 to 3 is messed up? Well, and it really comes down to the interval from 1 to 3 includes both what? Positive velocity and negative velocity, right? Mm-hmm. So I have written down here that no, my explanation was that velocity increases where acceleration is positive.
Velocity increases where acceleration is positive? I mean, that makes sense not to explain this, though. It would be the opposite, wouldn't it? Velocity decreases.
Because the difference in the intervals is the
it'd be velocity
1 to 2.
Positive when acceleration is decreasing, wouldn't it? Not velocity is increasing. Velocity is not increasing on that interval.
Well, okay. So I don't think I was necessarily, I'm trying to think what I was thinking when I wrote that. I don't think I was necessarily referring specifically to that 1 to 3 interval. Now that I look at that. Which way? Okay. Velocity increases where acceleration is positive.
I mean, yeah, that's true, I guess. Velocity increases. Yeah. Because from 3 to 5, acceleration is positive and velocity is increasing.
Yeah. That's probably where I was referring to it. So I'm going to go with, there's not just going to be one way to explain this. There's going to be several ways you could explain that for sure. Okay. We're ready for 9?
Mm-hmm.
How fast is the particle moving at time t equals 4, and in what direction?
Negative 5 feet per second. And it would be going left since it's negative.
Okay. I'm going to tweak one thing. Since they use the word, how fast is the particle going? What are they referring to?
Speed.
Okay, since they use the word how fast, they need you to reference speed. And we talked earlier that speed is the absolute value of velocity. They want to know the velocity at time 4. So speed is the absolute value of velocity at time 4. And realize this is a velocity graph, yes? So velocity at time 4 is just looking approximately right there. Okay, and that's at -5, but the absolute value of -5 is 5. For whatever reason, I don't have the units on most of this paper, I'm realizing. And it did give units, didn't it? Yeah. So we could say that is 5 feet per second. And in what direction? Because velocity was negative, it would be moving in a negative direction or left here. Because they did say along a coordinate line.
So then you just, the velocity is -5 feet per second.
For the next one? Yeah. I don't know why. I feel like these questions are backwards. What is that should have been asked in the opposite order. What is the particle's velocity at time t equal 4? Well, that's just asking, what is the velocity at 4? Find that point on the graph. And that is -5. And again, the negative indicates it's moving in a negative direction, so probably left. Okay. What is the average time, velocity over the time interval 2 to 3?
Well, isn't that just acceleration? Average velocity over time.
Well,
it'd be like v1 minus v2 over t.
Except,
minus v1.
So in order to get average velocity, you're doing basically the slope, not of velocity, but you're doing the slope of distance. So we're actually, in order to do this average velocity, we're going to think about the change in distance over the change in time. Because when we talk about average velocity, you're thinking about what would be the slope of a distance scenario. And that might not be the best way for me to explain it based on the look on your face, but that's the way my brain goes with it.
Yes, do the math.
I guess I'm thinking AROC in a way, and so you're looking at the change in distance over time. Now, with that in mind, how do we find the change in distance on a velocity graph?
Area.
That's going to be the area. So remember, total distance traveled is area under the curve.
-5 feet per second again. Which is also the slope of that line, which is what I was saying.
Okay. And I guess
because acceleration is equal to the change in velocity over time, which is the slope of the line.
Okay, I see what you're saying.
Because if you look at that slope, you're going to get the same answer.
Okay.
It's -5.
Okay.
That's just the way we're taught.
I get it. And this is where your physics is definitely more recent than my physics. So I was looking at it as, okay, so the change in distance over the change in time is velocity, average velocity. And so we need from 2 to 3 is the time interval we were working with, right? So we have this lovely triangle. In order to do the area of that triangle, 1/2 base times height. So 1/2 times 1 times -10 is what we're looking at there. So what I was going to have on top here is 1/2 times 1 times -10. The change in time, that's 3 minus 2, which is 1. So you do end up with -5. And that would be feet per second. And you said you looked at it as
the slope of the line. Because velocity over times the change in velocity over time is acceleration.
Okay. Okay. I'm there. As I said. Excuse me. Okay. 12. When does the particle change direction?
T equals 2.
And t equals 2 because that is an
Well, it's just
x-intercept.
Velocity goes from positive to negative.
Yeah, velocity goes from positive to negative. Graphically, it's your x-intercept on a velocity graph. So whichever way you want to think about it, x-intercept or velocity changes from positive to negative in this case, or it could be negative to positive. So we said x equals 2. Excuse me, not x. T equals 2. Okay. How far does the particle move during the first second and which way?
5 feet to the right.
Okay. So that first second is when you have that horizontal slope, yes? Okay. So in 1 second, you're moving 5 feet per second, and so that is 5 feet. I'm assuming you multiply there again in your brain? Yeah. Okay, so 5 units right. I don't know why. I did not use a lot of units in my notes, and I'm assuming I overlooked the units in the label up at top, so I agree. Okay. How far to the right does the particle go, and when does it arrive there? Wait, what?
It'd be 7.5 feet. It arrives there at 2 seconds.
Okay, and I was not understanding the question, which was what my what was. How far to the right does the particle go? Well, when does the particle move to the right? When velocity is what? Positive, right? So this section here, yes? And so with that in mind, I'm going to say area under the curve. We already know there's 5 here, and then this is half of 5, so that area under the curve is 7.5. So I think I wrote mine as like the fact that there was a 5 times 1 for the square or rectangle, and then there's a 1/2 times 5 times 1. So if you're thinking area, 7.5 feet, and that is at t equals 2 seconds. And we know it's at t equals 2 seconds because that's the x-intercept again. Okay. 15. Total distance traveled by the particle.
7.5 feet to the left.
Disagree. You're one question too soon. Total distance.
Oh, it'd be 22.5 feet.
And why 22.5 feet?
Because it travels 7.5 feet right and then negative 15 feet.
Okay.
Left.
So this was 7.5 over here. This triangle here is 1/2 base times height, so 1/2 3 times negative 10. So that area is negative 15. Total distance is just it traveled 7.5 right and 15 left. Those are both distances traveled. So 7.5 plus 15, which is 22.5.
Distance versus displacement.
Mm-hmm. And you do have to be very careful. Okay, total distance, you're adding positives and negatives together like the signs aren't there. Displacement is, okay, what's the distance from your beginning point to your ending point? Doesn't matter how many laps it took you to get there. Okay, so 16, what's the particle's position after 5 seconds?
7.5 feet per left.
Okay, and this is, would you call this displacement then?
Mm-hmm.
Okay, so this is what we would refer to as placement because they just want to know how far were you from your beginning point.
Or the
Okay.
change in distance, I guess, is what they would.
Right, so
It'd usually be like delta x in physics or delta s in this, I guess.
yeah, so displacement or what was I going to say? Oh, change in distance. Okay, so this is the fact that we went 7.5 right minus 15 left, oops, which is minus 7.5, which interprets to, when it says position, 7.5 feet to the left. Okay. Wow. Pretty much exactly finished 3 pages.
Yeah. I was hoping we were going to get a little ahead of it. But yeah.
I was hoping to get a little ahead of it too. Yeah, so that gives us 1 page of, still kind of a lot to do tomorrow. So, okay, 1 more day of notes in this lesson.